Hello, I'm Hassan Najafi, currently a PhD candidate at the University of Minnesota. My co-authors for this paper are my advisor, Professor David Lilja, Professors Mark Riddell and Kyo Wazaga. It's our pleasure to offer you our recent progress on stochastic computing, polysynchronous clocking, exploiting the skew tolerance of stochastic circuits. Stochastic computing is a re-emerging computing paradigm first introduced in 1969. In this paradigm, logical computation is performed on random bit streams. The value is represented by the probability of obtaining a 1 versus a 0. Implementing complex operations with simple hardware and high noise tolerance are the main advantages of this paradigm. High latency and high energy consumption, however, are the main weaknesses of computation on stochastic bit streams. The energy consumption of stochastic systems is often more than that of their corresponding conventional binary implementations. So, the main motivation of this work is to mitigate these weaknesses. In this work, we introduce a more compelling advantage to stochastic computing: tolerance of the skew or different arrival times of the clock signal or the input data. We show that in stochastic circuits, the correct value is computed even when the inputs are misaligned temporally. Here we see an example of stochastic multiplication using an AND gate with unsynchronized bit streams. As shown in the figure, the value represented by the output bit stream is 0.3, the value one expects when multiplying 0.6 by 0.5. Synchronism brings significant advantage to digital systems. It simplifies the design effort and guarantees the performance. However, it comes at a significant cost. The system requires a clock distribution network. These networks cost area, consume power, and most importantly, limit the performance. Exploiting the skew tolerance of stochastic computing, we introduce polysynchronous clocking, a design strategy for optimizing the clock distribution network of stochastic systems. Clock domains are first split at a very fine level. Then we have two strategies. First, we synchronize each domain by an inexpensive local clock, such as an inverter ring. This obviates the need for an expensive global clock network. Second, we can keep the global clock distribution network but relax the clock skew requirements. This allows for a higher working frequency and so a lower latency. As a case study, we implemented a stochastic Roberts cross edge detection system with 16, 64, and 256 cells to parallel process an end-by-end input image. We evaluated three cases. First, the conventional synchronous approach with a global clock distribution network that synchronizes all cells. Next, we remove the global clock network and instead use locally generated clocks for each cell. Finally, we synthesize the system with a relaxed clock distribution network. Here we compare the savings due to using different approaches of polysynchronous clocking. The reduction in delay is the most significant benefit. Even with a relaxed clock distribution network, the benefit is significant, although not as great as with removing clock distribution network and using locally generated clocks. In terms of area, both approaches decrease the cost. For larger scale systems, removing the clock distribution network provides more area saving. However, for smaller systems, relaxing the clock network is the better approach. As shown, removing the clock distribution network results in overall energy consumption reduction, except for a small 16-cell circuit. For this circuit, the local clock's power consumption outgrows the power savings obtained by eliminating the clock distribution network. So in this work, we introduce a skew tolerance of stochastic computing circuits. From basic stochastic operations to complex circuits, the correct output is computed even when the inputs are not synchronized. We propose polysynchronous clocking, a design strategy for exploiting this skew tolerance. We discussed and evaluated two design strategies: removing and relaxing clock networks. Replacing a global clock network with local clocks significantly improves area, latency, and energy consumption of large stochastic designs. For smaller systems, however, a relaxed global clock network is a more efficient choice. By referring to paper, you can also see that the circuits designed with either of the polysynchronous approach are as tolerant of error as the conventional synchronous stochastic circuits. We hope you found this interesting. For more details, please refer to the paper on the IEEE Transaction on Computers website. Thank you.